So we already saw that phenols are acidic and alcohols are not. Now let's also try to understand reason why is it so. The cause is owing to either destabilization or stabilization of alkoxides or phenoxides. Alright, so let's try and understand how destabilization and stabilizations are the cause of acidity for alkoxide and phenoxides. Okay, so let's begin with alkoxide. ROH, alcohol in water, assume it dissociates into RO minus and H3O plus. H plus from H goes to water and forms H3O plus. Alright, now is this stable? It is not stable because we have studied about inductive effect. What is inductive effect? Let's understand that first. Plus I effect. Plus I effect is electron donating property of a group is plus inductive effect. And examples are methyl, ethyl, propyl, butyl. All those alkyl groups are one of the best I plus. One of the best electron donating groups. Alright, so they have very high plus I value. Now let's talk in terms of minus I effect. Obviously, if this is electron donating, this has to be electron accepting. So it's electron accepting property of a group. We have Cl, NO2 and many other which are all electron withdrawing groups. Alright, now what happens here? Coming back to our molecule, what happens here? Here it's alkyl group, methyl, ethyl, propyl, butyl. So we saw that it has plus I effect, owing to which what happens is it destabilizes the alkoxide ion. Alright, so it destabilizes the alkoxide ion. Owing to destabilization of RO minus ion, does not ionize much in water. So alcohols do not ionize much in water owing to destabilization of alkoxide ion. Alright, and why so? Owing to plus I property of R group. Alright, okay, now let's understand what happens in case of phenols. In case of phenol when put in water dissociates to phenoxide and H plus ion, which is abstracted by water to form H3O plus ion. Alright, now in this case what happens is this negative charge is stabilized by phenoxide via resonance. Now let's understand a bit of resonance now. This is how resonance works. Now this is the phenoxide ion, this is the phenoxide ion. So what happens is the electron shifts over here, then this bond which is there, it shifts over here, giving negative over here. This negative again shifts over here, and then this bond shifts out over here, giving negative to that. This shifts over here, so new bond is formed over there. This bond shifts out over there, giving negative charge over here. Then once this negative charge is there, it comes to this place and this goes back to its original place. So 1, 2, 3, 4, 5 resonance structures. The more the resonance structures, more the stability the phenoxide would possess. So if resonance structures are still more than this, that would be more acidic. Alright, so therefore phenol ionizes to moderate extent in aqueous medium. So I told that if there are more resonance structure than these, then those molecules, those phenols would be still more acidic. Let's choose one of such molecule. Okay, that is nitrophenol. Okay, now let's see what happens in nitrophenol. Now let's try and understand what happens in case of nitrophenol. Nitrophenol, when put in water, it dissociates into phenoxide and H3O plus, as we saw in case of phenol. Now let's understand resonance structures, because if it has more number of resonance structures, then definitely nitrophenol would be more acidic than phenol. Let's check it out. Now see, here what we see is the same story that we observed in case of phenol. This goes down over here, oxygen satisfied with its 2 bonds, so no charge over there. This forms a bond, then this carbon gets 1, 2, 3, 4 and 5 bonds, so this pi bond has to shift out over here, giving negative charge in ortho position. Now then this goes down again, and as it goes down again, this comes here and gives negative charge over here in para position. All right, now what happens is something different. Now this electron cloud is migrating out of the ring. Now it goes to nitrogen. Now as it goes to nitrogen, so nitrogen forms double bond now, nitrogen forms a double bond now, and this bond shifts out. And I hope you are understanding this all happening. The shifting of bond is all happening just to keep its every atom's required bond intact. Now for example, if I shift this over here, if this electron, for example, if this electron is shifted over here, then this nitrogen would have 1 newly formed bond, 2, 3, 4, 5 bonds. So not possible. Pentavalent nitrogen, not possible. Already it has positive charge. It has 1 excess bond owing to which it is positively charged. So the bond has to quit nitrogen. So the bond pair has to quit nitrogen, all right, and move over oxygen. So that's the reason why these shiftings are occurring. All right, so anyways, let's get back. So let's continue. So this shifts over here. So see, oxygen gets negative charge, then again oxygen, again this electron is returning back now to the ring, returning back to ring. So it comes back over here. As it comes back over here, taking its original position, this shifts over there for the same reason that I told about number of bonds. Okay, so it shifts over here, so this bond is formed. As it shifts over here, this bond shifts over here, negative charge in ortho position. All right, then that moves in here and this goes out there, so we get back the identical structure. All right, so there we had seen there were 5 resonance structures, whereas here we see 1, 2, 3, 4, 5, 6 resonance structures. More number of resonance structures, so more the number of resonance structures than phenol, more the acidic it would be than phenol. Okay, that's the reason why whenever you are putting in some electron withdrawing group, this becomes more acidic. Phenol becomes more acidic. More the electron withdrawing group, more the acidic phenol would be. All right.